Welcome back. This will be lecture 16 of EC253C. In last few lectures, and in fact, last few lectures, we discussed about various concepts related to the AVR programming, AVR microcontroller programming. We have discussed the jumps. We also know that jumps can be of two types: conditional jumps. Those which check certain conditions before jumping to a particular location. For example, BREQ. In this instruction, Z flag is actually checked. And also then we had unconditional jumps. We discussed three unconditional jumps: jump, I jump, and R jump. What was the difference? The difference was the way in which they get the target address, the way in which they receive the address of the target. So we have jump, JMP simple jump, we have R jump and I jump. Also, we have discussed various instructions pertaining to moving data or from one point to another point inside the microcontroller, or also some of the arithmetic instructions were discussed. So we also discussed various instructions like LDI, LDS, add, in, out. And in last Zoom discussion, we saw that using these instructions and using the knowledge so far we have gained in this course, we were actually able to demonstrate an embedded system which has LEDs, which had 8 LEDs, and we were constantly able to blink those LEDs. So we wrote a program to blink LEDs connected to a particular port. Atmega 328. For that, we discussed the various ports associated with Atmega 328 microcontroller and how we can send data out of any port, and how we configure ports, and how then we send data outside the port. Before discussing more things related to the input output of Atmega 328 microcontrollers, we must first discuss call instructions. Call. As was the case with jump instructions, is another control transfer instruction. Sorry. Control transfer instruction. Which is used to call a subroutine. And what is a subroutine? Subroutine is the same thing as functions, what we call functions in high level programming. A bunch of code written somewhere else that is used frequently in a program, and whenever we need to execute those few instructions, those couple of or more instructions inside that block that's written somewhere else, we call it, and that's known as calling a function or calling a subroutine. And why we do that? It actually saves us the memory because it's used more than once inside a program, so we write it only once, and whenever we need it, we call it. We have three call instructions, in fact 4 call instructions in microcontrollers. We have call, simple call, and this is known as long call. And again, like jumps, we have OR call, relative call, we also have I call, indirect call, and then we have one more that's known as extended indirect call, EI call. These are the mnemonics used: call for long call or simple call, R call for relative call, I call for indirect call, and EI call for extended indirect call. Again, what's the difference in these four? It's how the target address is calculated, how the address of the subroutine which we have to execute is calculated. In case of long call, the address is given inside the instruction itself. Instruction contains the address and we jump to that address. Our subroutine is written starting from that address. In case of relative call, the address of the subroutine is calculating by adding a particular number that is present inside this instruction to the contents of the program counter, and the result gives us the starting address of the subroutine. In I call, as you may have seen in I jump, the target address, the address of the subroutine, the starting address of the subroutine is written in a special register known as Z register. In extended indirect call, we have another register that's actually the contents of which are actually added to the Z register before calculating the target address, before calculating the starting address of the subroutine we need to execute. So first we will discuss the simplest of ones, the call. It's again a 4-byte instruction, that means 32 bits, 4-byte instruction, in which 10 bits, first 10 bits, they are used for the opcode, and the other 22 bits, that means from bit 21 bit 11 to 32, they are used for the address. So address of the target subroutine can be anywhere in 2 raised to power 22 words address space, that means 4 megabytes bytes, or this may be words because it's word addressable. So 2 to 4 multiplied by 2, that means 8 megabytes memory. Anywhere in the 8 megabyte memory space we can have the target address. We can jump using this call, long call, we can jump anywhere in the 8 megabyte memory space of a microcontroller. Of course, Atmega 328 doesn't have 8 megabytes, but some of the members of the AVR family, they have up to 8 megabytes of memory, and we can jump using this call instruction. Using this call instruction, we can jump anywhere in that 8 megabyte memory space. So for example, our sample program can be something like this. Let us repeat the program we have used earlier. The program we used to blink the LEDs of our microcontroller. a port B. So I think this was the program. First of all, using this instruction, we configured port B as an output port, and then we send 255 all ones to the port B, and after that we also immediately after that we send all zeros to the port B. So when we sent all ones, the LEDs connected to the port B, a voltage drop was created across those LEDs and they were turned off on. And then after some time, when we send all zeros, the voltage drop across the LEDs was 0, so they were turned off, and then the cycle was repeated. But there's a catch in this whole program. How fast or how quickly will this LED blink? For how much time it will be on, and for how much time it will be off? That will actually depend on a couple of factors. One of them is the crystal frequency. That's attached to AVR microcontroller. In fact, if you remember in the last class, I told you that we connect a crystal oscillator to the pins 9 and 10. What's the job of this crystal oscillator? It provides timing for our microcontroller. So the time our microcontroller takes to execute each of these instructions will actually depend upon the value of this crystal oscillator. And the second thing on which the rate of the instructions, the rate of the execution of instruction depends. It also depends upon the internal architecture of the microcontroller. What's the exact IC technology we have used, or what's the exact technology of the processor we have used. For example, in the Harvard architecture, we have separate data memories, and this data memory, this processor, and separate data memory and code memory. So since we have code is written separately from the data, we have separate buses. So naturally it seems that this type of architecture will be faster than one Neumann architecture, because both code and data are written in the same memory, and we have the same bus to access both code and memory. But here, since we have two different memories, two different buses, so we can do this simultaneously. At the same time, we can the processor can fetch a piece of code to be executed, and at the same time it can fetch some data to be executed. So it depends upon a couple of factors. One of them is crystal frequency, and then there is the exact technology which has been used. We may discuss this thing maybe in more detail in this lecture or maybe the next. So what's the point here? That each of these instructions takes some finite time to execute. That what will be the order of that the time? Let's assume the most commonly used crystal oscillators are somewhere between 10 megahertz to 20 megahertz in AVR microcontroller, or maybe more than that. But most commonly we use somewhere maybe 16 megahertz, 24 megahertz crystal oscillators. So a crystal oscillator, that's, for example, if we take 10 megahertz, the time period will be equal to 1 divided by 10 into 10 raised power minus 6. That means 0.1 microseconds. Most of these instructions will take only one machine cycle to execute. And what's the machine cycle? It's the smallest amount of time that's needed by the CPU to do a particular job. And in case of AVR microcontrollers, machine cycle is equal to the frequency of the crystal oscillator, or time period of the crystal oscillator. So here, if we have attached a 10 megahertz crystal to my AVR microcontroller, to the Atmega 328 microcontroller, in which I have burned this program of blinking LEDs connected to the port B, what will happen? Each of these instructions will take 0.1 microseconds to execute. In fact, some of the instructions like jump or other instructions, they take a bit longer, maybe 2 microseconds, maybe 2 machine cycles, and that amounts to 0.2 microseconds. But we can assume for now that each of these instructions takes only 1 machine cycle, and in case of AVRs, machine cycle is equal to the time period of the crystal oscillator, and we have assumed that we have attached a 10 megahertz crystal to our AVR microcontroller. When we write the program, then burn it, finalize the hardware and start the program, what will happen? First instruction, this will be executed and it will take 0.1 microsecond. This will be executed again, it will take 0.1 microsecond. When this instruction will be executed again, it will take 0.1 microsecond. After that, this instruction will be executed. That means port B, the pins of port B will get a 5 voltage, and this, it will take us 0.1 microsecond to execute this instruction. And what will happen after the execution of this instruction? The LEDs will turn on. But now the question is, for how much time these LEDs will be on before turning off? That depends on how fast the next instruction is executed, which turning them off. How quickly is the instruction that's turning them off executed? So what's the time gap between the instructions of turning them on and turning them off? And how to calculate that? By the end of the execution of this instruction, out port B R17, our LEDs will be on. After that, we have this instruction. We are loading a value in R17 and it will again take 0.1 microseconds to execute. Still our LEDs are on. And after that, we have this instruction, out port B R17. Whatever is in R17, that is all zeros, are outputted to port B. And with the execution of this instruction, our LEDs will be turned off. That means after turning on, our LEDs will be on only for 0.1 plus 0.1 seconds. That means, sorry, microseconds. That means our LEDs will be on only for 0.2 microseconds before they are turned off again. And similarly, when they are turned, that means I can say that T on time is 0.2 microseconds. And roughly we can assume that T off, because after a couple of instructions, again our we turn off, we turn them back on, and the cycle repeats. So we can assume that T off is also 0.2 microseconds. So we have something like this. LEDs are turning off by high. We have a square wave at the pins of port B. And T on is 0.2 microseconds and T off is 0.2 microseconds. The point here is, can we visualize this? An LED is blinking at a frequency with a time period of 0.4 microseconds. Sorry, microseconds. That means at a rate of 1 divided by 6. (25 into 10 raised power 4), that means 250 kilohertz or 0.25 megahertz, or 250 kilohertz, that means 250 into 10 raised power 3 hertz, that means 250,000 times in a second. LED is blinking at a rate of 250 kilohertz. That means it's turning on and off 250,000 times in a second. Can human eye visualize this? Of course, no. We can't even visualize uh, the rate of the AC which is coming to our homes at 50 hertz. So it is impossible to visualize it. LED is blinking. Of course, it is blinking. It's turning on for some time, then turning off for some time, turning on and off. But we can't visualize because it's going at a very fast rate. So what we normally do if we had this kind of objective in mind that we have to turn LEDs on and off for some function, what can we realistically do? What we need to do, we need to incorporate delay between instructions. For example, after turning the LED on, we might incorporate a particular delay here, and after turning them off, we again may incorporate a delay here. So delay. Now the question is, how do we incorporate delays? In assembly language programming. How do we incorporate delays in assembly language programming? There are again a couple of ways to incorporate delay. We can use timers. That's a very good method. But since we have not discussed timers yet, we incorporate delay by doing some sort of some useless thing which has no objective. For example, if you remember correctly, we have an instruction that is known as NOP, and it does nothing, no operation. NOP, no operation. But what it does, it wastes CPU time. How much time? Again, only 0.1 microseconds, because CPU will need only 0.1 microsecond to execute this instruction. So let me rewrite this program. This one. What's the objective here? We again want to delay. We again want to actually blink LEDs, but this time we need a realistic delay in between so that human eye can perceive the blinking of these LEDs. The hardware is same. We connect the LEDs, but we need to rewrite the program. So let me do it something like this. The original program was something like it. LDI. We have used a register R16 first to configure the ports, so I have moved ones into it, then out DDRB R16. After that, what we have been doing, we have used another register R17, some data in it. For example, we have to turn them on, we have to turn LEDs on, so all ones, and then out this data also, but this time to port B, so that these ones will get displayed on the pins of the port. Then after here we since when this instruction will be executed, output be R17, LEDs will be turned on. After that we need to wait, so let me put some space here, and after that we again need to turn them off. So this time maybe I will use one more register. Maybe I will write LDI R18 0,00 and out LDI out port B R18. After that I need to jump jump to ABC, and my ABC is here. This time I don't need to reload R17 because I have used two different registers for turning the LEDs on or sending ones, and for sending 0 I have used another register R80. So I will jump here. Sorry, one more thing. Before jumping I need to keep the LEDs off for some time. So my jump will not be here. There again will be some instructions which actually will create that delay. So maybe my jump will be here, GMP to ABC. So what will now happen in this program? The program is same. I am configuring my port as output port. After that I am loading ones to that port so that the LEDs will be turned on. But this time after turning them on I am writing few more instructions that will actually give some time delay, maybe time delay of few microseconds or few milliseconds or maybe a second or half a second, which so that the human eye can perceive that the LED has turned on and it's on, and then it turns off. After that I'm turning the LED off again, and then again some delay again so that we can see that the LED is actually blinking. Then I am repeating the whole process, turning them on, delay, off, delay, again and again. So how can we incorporate delays here? As I have said, we use NOP, no operation. So I can write NOP here. I can write NOP here. Previously, since it was taking 0.2 microseconds, the LEDs were on for 0.2 microseconds and then they were off for 0.2 microseconds. Now, since I have written an NOP here, no operation. So, after the LED is turned on by this instruction, there are 3 instructions in between, and this instruction, it does nothing. It only wastes time. The CPU executes it, and it takes CPU 0.1 microseconds, and that 0.1 microseconds actually wasted. So, but this time, since there are 3 instructions in between before the LED is turned off again here, so the time period of the blinking has increased, and the frequency of course has decreased. How much? By 0.1 microsecond, that means 0.3 microseconds, but still it's not enough. So what we can do, we can actually write this NOP many times, maybe 1,000 times, or 5,000 times, or 10,000 times, or 100,000 times. Maybe if I have written it 10,000 times, so the total time wasted, total time of the CPU wasted will be 10,000 into 0.1 microseconds. That means 1 millisecond. And if I use this NOP maybe 100 lakh times, 100,000 times, or 10 lakh times, what will happen? I will have a time delay of 0.1 seconds, but I have to use it after both the instructions of turning it on here, turning off here, and then after turning the LEDs off. So by doing that, I will actually increase the time period of the blinking, and so that the human can perceive this blinking. Now the question is, I can't in fact write it NOP 5000 times or 100 times. That will waste a lot of programmer effort and also a lot of read only memory where I burn the program. So what we do, we use jumps, conditional jumps. We use a counter, a register, as we have discussed earlier, a counter as a register. Then that counter is decremented and checked if we have reached 0 or not. If we have reached 0, we go out of the loop and execute the instruction after that. Let me try to do that. Of these instructions. First, I need to use a general purpose register as counter. I have used R17, R18, R16. Maybe I use R19 here. So what I will do after turning the LED on, I will actually execute a statement which doesn't do any job, no operation, maybe 100 times or maybe more. Since the limit for a simple loop is 255, we can execute it a maximum of 255 times. If we need large time delays, we use nested loops. Let's begin with using a simple loop. So what I will do here, LDI, I will load a register R20 with a maximum value 0 cross FF. Then for example, I will write NOP, no operation, and then decrement R30. B branch if not equal to, that means branch if not equal to 0, that means branch if the 0 flag is not set to, we have used the label ABC, so we use some other label, maybe XYZ, so it will jump here. Okay, and execute this piece of code 255 times, FF times. Again here I will use another register, LDI R21 0 cross FF, or I can use same register again, maybe R20. NOP, no operation again, decrement, or this was on R30 or 20 or 20, and branch if not equal to, this time we won't even use XYZ, maybe something else, maybe AB or maybe XYZ1. So we will branch here to NOP again, XYZ1, XYZ1. So this is my whole program. I am configuring the port. Here I am configuring the port configuration. Then I am turning the LED on. LED is on. Then I am incorporating this delay here. then I'm turning the LED off. LED is off. And then again the delay, and this instruction is used to repeat. So my program is very similar to the previous program, but what we have done here, after turning the LED on, we are keeping the LED on by incorporating a particular delay between turning it on and turning it off. And again, after turning it off, we are again incorporating some delay so that it will be off for some amount of time. What exactly will be that time? That will again actually depend on few things, like the crystal oscillator we have connected, and then how much time does each of these instructions, how much machine cycles does each of these instructions take. As I have told, most of the instructions take only one machine cycle, but there are some instructions like jump, branch, which have to calculate the address, jump address or branching address. They take more than one machine cycle, sometimes two, sometimes three machine cycles. If we assume that each of these instructions takes only one machine cycle, so what we are doing actually inside this delay, I am loading some value. So this instruction, this instruction, the first instruction, it is executed only once. Then I am executing an instruction, no operation. How many times this will be executed? Since it's inside that loop, because we decrement this R20 register, then check if R20 has reached to 0 or not. If it's not reached to 0, it will again jump to XYZ and execute these two instructions again. So actually these three instructions are executed again and again, and how many times? FF times, since up to when R20 will reach 0. So what will be the approximate total time delay, assuming that each of these instructions takes only one machine cycle, and also assuming that we have a 10 megahertz crystal connected to our microcontroller, and that gives 0.1 microsecond machine cycles. So the total machine cycles wasted will be actually 0.1 multiplied by 3, because we have 3 instructions, multiplied by total number of times these 3 instructions will be executed. That is 255. That means 15 0.1 0.7, sorry, 3.15 76.5 microseconds. That means the LED is on for 76.5 microseconds, and then LED is off again for 76.5 microseconds. Of course, we can increase this time delay by maybe writing few more instructions inside it, or the better way is to use the nested loops, to use a loop within a loop. So if we have 3 instructions that take 0.3 that takes 0.3 microseconds to execute, and they are inside 2 loops, so the total time delay will be 0.3 microseconds multiplied by 255 multiplied by 255. The maximum time delay we can incorporate using two loops is 0.3 multiplied by 255 multiplied by 255 microseconds, and that amounts to approximately 19.5 milliseconds. And we can further increase it by using another loop, by using 3 loops. So again, our time delay will be multiplied by 255, so we can get maybe a time delay of approximately 4.9 seconds. So we can get a lot of time delay, and we can realize the blinking of the LEDs. This we are discussing the concept of call instruction. I told you that call instruction it's also a type of control transfer instruction, and we have 4 call instructions. We have call, long call, R call, I call, and EI call. We'll be discussing each of them in detail. This time we were discussing the simple call, or what we call as long call. It's a 4-byte instruction. 10 bits are used for opcode and 22 bits for address. And this program I showed you how we can incorporate a call or a subroutine inside a program. As you can see from the program, this piece of code, the piece of code here, and here, it's used twice in the program. So what we can do, we can write this piece of program somewhere else only once, and then we can call it whenever we need it. For example, I can write this program maybe like this. I started with configuring the port LDIR16 0x FF out DDRB R16, then turning the LED on LDI R LDIR 17 0x FF, and then out R7 out port B R17. Then I have to call the delay subroutine, which I will write somewhere else. I can simply say call, and I have to name that, like I label my instructions when I have to jump. Here I also have to label the first instruction of the call subroutine so that I can call it whenever I need it. So maybe I can give it any label, maybe ABC, or sometimes I give it a label that specifies its function. So I can use a label delay here, DELAY. I have yet not discussed or yet not described this delay function. That we will do later. And after that I will again do LDI R18, turn the LEDs off, 0x00 out port B, and it was port B, port B R18. Then again this delay, I will again call the same function if I need same amount of delay. Then I have to repeat the process, jump ABC. So ABC will